are axioms, and probability of A is 1 minus probability of A complement. So this is the first property. Right? Remember, A complement is what? A complement is the set of all elements in the universe, sample space, minus A, right? Minus A. So the proof is fairly straightforward. So we know that probability of A intersection A complement is empty. So there's nothing in common between A and A complement. And also A union A complement is the entire sample space, right? Okay, there's nothing going on there. So here are the three axioms. So if A1 intersection A2 is empty, then probability of A1 union A complement is just the sum of the probabilities. And that's exactly what we're going to apply to these two sets, A and A complement. So because A intersection A complement is empty, we know probability of A plus probability of A complement is just probability of the full sample space, and that equals 1 by axiom 2. So then we just simply rearrange. So 1 minus probability of A complement is probability of A. It's the direct consequence of the axioms. Okay, that's all this is saying. And so when we look at our little example, probability of head is 1 minus head complement, which is probably 1 minus probability of tails. Okay. So property 2 says the following. If I have any two events, A and B, then probability of A union B is simply probability of A plus probability of B minus the probability of A intersection B. Right? So this is basically, here is a generic picture, sort of proof by picture. So here is event A, event B, they're both subsets of capital omega, and maybe there are some little omegas that are in the intersection of A and B. Okay. So all we want is probability of every element in A union B, right? So once again, this is just probability of A plus probability of B, but we've double counted the intersection, right? Once in A, once in B, so we just subtract the intersection once. That's all that's going on. And of course, if A and B intersection is the empty set, then this is still going to be probability of A plus probability of B minus probability of the empty set, which is 0. It still holds for non-intersecting events, just joint events. Okay, so then we're done. I mean, we introduced probability axiomatically. We saw a couple properties. So now what we're going to do is start looking at computer representations of this mathematical concept, right? So this is mostly somewhat pedagogical, but I think it's not a bad idea. So we're going to define our own class called ProbMap, okay? And this is sort of throwing you in the deep end of Python classes, but don't worry about it. You don't need to fully understand it, but the main thing is I want you to get a feeling for how straightforward it is to implement this notion. So here's my class, ProbMap, and okay, so it has some initialization for a constructor, and then it has some things called sample space set. It creates the set out of a sample space. It does some asserting, which is to check things are right. And it asserts that the probability sum, which is the sum of all the elements in my probability list, is 1. And there's things like this. This one returns the probability of an event, the definition P, which is inside the class. And then it has a method to output the string, and it can get the probability map, and so on. Right? So there are some other methods defined on this. So let's kind of see this in action. So this is, so we've already seen natural numbers and integers, and they're all classes implemented in Python or SageMath. So here is our example. So we can take this experiment with the fruit bowl. So 2 oranges, 3 apples, and 1 lemon. All right. So we're going to stick our hand inside the fruit bowl and pull a fruit at random. So here the sample space is orange, apple, and lemon. And then the way we're going to do this is first create our sample space as a list of these 3 strings. And then we also want to define these probabilities for, because there are 2 oranges, 3 apples, and 1 lemon. We do them in the right order as the sample space list. So this is essentially the 2 ingredients we need, and then our prob map, the class we defined, takes as input the sample space and the probabilities, right? So probs and S space. So if we just do this, we would have constructed a probability map for us. So it's simply the little omegas, the outcomes mapped to each probability. So you can do dot p of lemon, which is 1/6, so it's just simply calling what we put in. But we can also give it p of the list of lemon and orange. So this is the fruit being a citrus, that's half, and so on. So here's a set of all events. So we don't want to do this for a very large sample space because it'll be too big. But I'm just simply using this method called subsets. So this returns the set of all subsets of the sample space. And I'm simply listing all the subsets. So here's the empty set. So nothing happens event. Orange, apple, lemon, orange, apple, orange, lemon, lemon, apple, orange, lemon, apple. So we should have 1, 2, 3, 4, 5, 6, 7, 8. So do you see why there are 8?
2 to the power 3.
Yeah, so 2 to the power 3, right? This is the set of all, because there are 3 elements in the subset. So it's the set of all subsets of the 3 elements. So do you know why this is 2 to the power of 3?
Because with 3 elements, we can have maximum 8 different kinds of combinations.
Yeah. Yeah, that's right. So I mean, but the logic for this is what?
Each event can either be in or not be in.
Yeah, exactly. Exactly. Yeah, so your mapping, is it there or not there for each of the 3 elements? So that gives you all possible indicator functions, right?
Like for second option, which is orange, it means apple and lemon are like present or something.
Yeah, that's right. So you can say, I don't know, so orange, lemon, apple, let's say is the order. Then, yeah, so the value 1, 1, 1, so true, true, true is the universal set. 0, 0, 0 is the empty set, and so on. Okay, and that's basically this power set example I was giving you. So 2 to the omega. So this prob map is really useful when the sample space is not too big, typically finite, so a lot of the concepts we defined can be implemented are implemented in this class and sort of available to you in an abstract way. So then I'm simply what's going on here? Maybe I can evaluate this. So I'm just marching through each of the events and printing, what's the probability of each event, which now makes sense, right? And this will satisfy all the axioms and so on. Okay, so let's work through this example 6 below for yourself. So this is from some textbook. I think this is my advisor's book. I took this from. So someone counted the occurrence of the alphabets in the English language by going through a big corpus of books. And here is the relative frequency of occurrence of each language. Okay. So here the thought experiment is I go to this corpus of books and I pick a book at random uniformly and then open a page uniformly and pick a letter uniformly. Then the probability I'll find a specific one of the 26 English letters is given by these relative frequencies. That's kind of the experiment under the hood. Okay, so it's like the fruit bowl, but it's just okay. So my alpha space I can say is A, B, C, D all the way to Z, and my relative frequencies are these numbers. I just hard coded it. Okay, so I can do that, and then I can do the same. Don't do subsets here because 2 to the 26 is going to kill us. Well, I don't know. What is 2 to the 26? It's really big. Well, you can try, see if it crashes your machine. Or... Okay, so this just gives me the probabilities for each letters in my prob map now. So that's the power of the class, right? Yeah, 2 to the 26 is huge, so we don't want to go through all the subsets. Although it's well defined for all these subsets, the probability map is well defined, but we don't want to enumerate through all of it. So for example, I can look at this event called vowels, A-E-I-O-U, and then I can ask what's the probability of vowels, right? So that's 189 over 500. That's pretty, it's almost 2/5. So yeah, I just made a little set, my own name. I don't have O, but I have all the other vowels. So you see, so I can do simple things like this. So try either adapting what we've done above or doing the same thing in some of the cells below to find the probabilities of other sets, letters, for example, your name. And if you're ambitious, you know, we have that little script that went and downloaded that book, right? Pride and Prejudice. So you can, for example, well, maybe later on, you can actually parse that entire string. And once we get into using dictionaries to count the frequencies, we can actually turn that entire textbook into a relative frequency counter and count all the English letters in that textbook and play the same game. Okay, so that's a nice thing about using classes. So next we'll get into conditional probabilities, random variables, loops, and conditionals. So once again, probabilities are just a certain kind of function from the set of events to 0, 1 that satisfy our 3 or 4 axioms. And they have these two properties. Probability of A is 1 minus probability of A complement, and for any two events A and B, probability of A union B is the sum of each probability minus the intersection ones. And this property too generalizes to n events, n arbitrary events, A1 through AN. And this is called the so-called inclusion-exclusion formula. So if I have n events, now the probability of the union of them is I first sum each of the individual probabilities, and then I subtract away the pairwise intersections once, okay, and then I add the three-way intersections once, and then I will subtract the four-way intersections and so on. These are those alternating, you know, this -1 to the power of n plus 1 term here. It's an alternating sum, so we have to basically correct for double counting and recorrect for triple counting and so on. So this is, yeah, I'm not proving this, but this is a generalization of this pairwise property. Okay. So does the inclusion-exclusion formula agree with the extended axiom 3? If A1, A2 up through AN are pairwise disjoint events, is the probability of the union equal to the sum of the probability of AIs? Yes, right? Because all these intersection terms are 0. Yeah, so then the domain of the probability function is the following. What exactly is stipulated by the axioms about the domain? So here we are getting into this more delicate land, right? So the domain should be what's called a sigma field in general. Then it's often denoted by the script F. So a sigma field is a condition on this set of events that we want to hold, so that this countable, the fourth axiom holds. So for a sigma field, what are the conditions? So it's called script F, or script F is just lowercase sigma of the sample space. This is my collection of events now. So it's called a sigma field. So the first condition is the sample space should be an element of the sigma field, okay? My collection of events. And if A is an event, that means A is an F, script F, then A complement should also be in script F. So that property is called closed under complementation. So anytime there's an event, then the complement of that event should also be in F. And then if I have a countable collection of events, A1, A2, ... all the way, countably infinitely many events possibly. If each of them are in script F, then the union of all of them should also be in script F. Right? So this is the sort of other thing you have to believe, right? If that holds, then script F is called a sigma field. If all these three conditions hold. Okay. Yeah. So we need to be aware of this, but we're not really going to do anything too hardcore with measure theory. But everything I told you about maps and inverse images and all of this stuff simply carries through here. Okay. So we'll just leave it there for now. Yeah, so that's my. So finally, we have the definition of a probability space, right? So the domain of the probability is not just any old set of events. It's rather a specific specific set of events that form a sigma field. That means the whole sample space is there. It's closed under complements, and it's closed under countable unions. That's how you say it. It's closed under means, yeah, the countable union is a set which is also there. And then formally you call this the probability space. So you have omega, which is my sample space, which contains all possible outcomes the experiment could have. And then you have a sigma field on it. So it's a triple, so the probability space is basically a triple. So this is my sigma field. And then there's some probability that maps elements here to values in 0, 1 and satisfies the axioms of probability. Okay, so here is again looking at the head and tail experiment formally. So this is, once again, the sigma field is sample space is there, the empty set is there, complement of head is tail, that's there, complement of tail is head, that's there. These are each other's complements, and then union of things here is also here. So for this experiment, this is the finest sigma field. So it's the finest sigma field because it cannot become any finer. And then this is called the trivial sigma field, right? Just the whole sample space and nothing. So, and for a fruit bowl experiment, the finest sigma field had 8 elements, 8, right? And once again, the trivial sigma field for our fruit bowl experiment is what?
4 or 9.
Yeah, exactly. So for the fruit bowl experiment, f of omega is going to be the three fruits, right? Apple, orange, and lemon, and then this. So of course there are other sigma fields between the most trivial one and the finest one, and as long as they satisfy the axioms of being a sigma field, they're allowed to be there. So in stats and probability, we have this notion of something called so in this case, let's say what do I call this, f prime, and f was the finest, right? So let's say f of omega is 2 to the omega, is the discrete experiment, that's the power set. So f prime of this is a subset of f, right? For these trivial, the trivial one is completely contained in this one, right? So more generally, there can be script f prime. This could be a subset of script f double prime, and this could be a subset of script f triple prime, and so on. And eventually, this will be a subset of 2 to the omega. Finite experiments you can think about. That could be a whole sequence of sigma fields where the amount of information is increasing from the most trivial one to the finest one. And this sequence is often called a filtration. You'll see it's used a lot to formalize exactly what can you observe in your experiment. Okay, so that's, yeah, so then we have probability space, as we just went through. The next main notion is called independence. So we say two events A and B are independent if the probability of A intersected with B is now the product of the individual probabilities. So this is just the definition of independence of two events, right? If you can explain the joint occurrence of A and B by multiplying the individual probabilities, then these two events are said to be independent. Yeah, and intuitively, this is how you'd say it in English. A and B are independent if the occurrence of A has no influence on the probability of the occurrence of B, vice versa. So flip a fair coin twice experiment. So now we don't toss it just once, we toss it twice and observe what happens. So I say the first flip is heads. Then the event B is let's say the event that the second flip is heads, and the event A is the first flip is head. Then probability of A is 1/2 because it is a fair coin, and probability of B is 1/2. And because the flips are independent, right? So we're putting the coin in this Percy's machine and just flipping them. Then you can just multiply them, right? Probability that the first toss is head, and second toss is also head is simply given by this multiplication because they're independent experiments. It's by construction. Okay. So we can generalize this by saying that we will flip a coin with an unknown probability parameter theta. So that's what I was saying here. We have unknown. We don't know what the bias of the coin is. So now we know it's some number between 0 and 1. And then we say that probability that the coin lands heads is theta. But it's the same coin we're flipping in the exact same way, repeating it. Then we can model it like this. Probability of head is theta, and probability of tail is 1 minus theta. Then it's exactly the same idea. So now, what is the probability of the event A that the first flip is head, and the event B that the second flip is head? So that is probability of A intersection B, and it's theta times theta, or theta squared, right? And if we have this event C, where the second flip is tail, then once again we have independence, but now we multiply theta by 1 minus theta, because this is the probability head the first time and tail the second time. Right? So once you start seeing this, so what is theta? Theta will be this line, right? And it's 0, it's 0, and it's 1, it's 1. So theta times theta is theta squared. So at half, we have a quarter, right? So theta squared. And So I don't know, something like this. It's theta squared. No? 1 times 1 is 1. Oh, yeah. What am I doing? So theta squared is what? Half is a quarter. Yeah, I did theta times 1 minus theta, I think. Yeah, sorry, this is theta times 1 minus theta. So theta squared will be quadratic, right? It will grow like this. Something like this. Quadratic goes under the linear curve, right? So basically, we are beginning to start seeing the. So when we keep repeating the experiment, right? So depending on what we observe, these numbers you're seeing, these will eventually become for us sort of likelihood function. So you'll start seeing that soon. So the same thing, if you want to roll a fair die twice, now the face is enumerated 1, 2, 3, 4, 5, 6. Then if it's a fair die, and same thing happens. So if A is the event, the first roll is 5, B is the event, the second roll is 1. Then we get probability of A is 1/6, probability of B is 1/6. And the first roll and second roll are independent, so I can just multiply the probabilities. So this is the power of experimentation, right? This is basically the birth of European Emperor system, right? So I can control the experiment, keep repeating it many, many times, and I can learn about nature, right? This is the primitive, right? And all you're doing is simply multiplications because your underlying experiment is under your control, so you just keep repeating it and learn more. This is a good video if you're kind of rusty about this, but maybe it's too boring. So the next main notion is conditional probability, right? So once we have notion of independence, so we can talk about conditional probability. So suppose that we are told that the event A has a positive probability of occurrence. So that means there is a chance it can happen. And what we are interested in whether another event B will now occur, given that A has occurred, right? So the way you think about this is that here's your full sample space omega. So what you know is A has occurred, so some little omega inside A has happened, right? So A has occurred. So now what you're interested in is this thingy, probability of B given A. Right? This is my conditional probability symbol with a pipe. So what I'm really interested in is shrinking my, my original sample space is omega, but A has happened, so I'm now shrinking my sample space to what has already happened, which is A. So probability of B given A is defined to be the joint probability of B intersected with A, so this part. And then now I have to divide it by P of A because P of A has already happened, right? So this is the idea of conditioning. Okay, so the sample space has shrunk from capital omega to A. And so the only the outcomes in B that also belong to A can possibly now occur because A has occurred. So what this means is now probability of A given A is going to be 1, right? We know A has occurred, so this is our new sample space. So this is P of A over P of A, which is 1. So if two events A and B are independent, then we have this nice relationship. So probability of B given A is by definition probability of B intersect A over P of A, which is nothing but the numerator. Because of independence, I can break it into P of B times P of A, right? So now the P of A's cancel, so I get P of B. So this is another way to talk about independence. So P of B given A is simply going to be P of B if A and B are independent, and B are independent. Okay. So here's a little example where we roll 2 fair dice. And the event A of interest is that the sum of the dice is 6. And the event B is the event that the first die is 2. Right? So then the question is, how many ways can we get a 6 out of 2 dice? Right? Because the first event says the sum is 6. Right? So I'm just enumerated all possible pairs, 1, 6, 1 through 6, right? So of course these guys, these painted ones, are the ones that where the outcomes sum to 6. So we know this event has happened. And my second event B of interest is that the first die is 2. So the first die is 2 only in this case, right? So it should be 1 out of 5, right? 6, 1, 2, 3, 4, 5.
Yeah, 1 out of 6 because we have 6 sides on the die, right?
No. So no. Yeah, you have 6 sides on the die, but this is all possible pairings of the 2 dice, right? So,
oh, okay.
But remember, my first event is that the sum is already 6. So remember what I'm saying is my first event A is this. You know, the sum of the 2 outcomes should be 6,
Okay.
which rules out the other possibilities, right?
All right. Yeah.
So now I have to figure out what is the probability of each of these events, these 5 specific events. But now it's an experiment with 2 tosses, right? So because of independence, you know, tossing them separate independently, this is 1 over 6 times 1 over 6, right? So each probability for each of these little outcomes is 1 over 36. So I have 5 1 over 36s, and I have to add them, so that's 5 over 36. So that's the probability that A will happen, you know. But then I'm given that A happens, right? My problem is I'm given that A will happen, and so my second die coming out to have 2 as the first entry, that's my event B of interest, right? So that's these possibilities. So all I have to do is sort of intersect that pink thing with this blue thing. I'm getting lost. So you see, this is all I'm saying. So event B is this. The event B is saying that the first die is 2. And what I'm saying is that event A has happened. So then the question is, what is the chance that, what is the conditional probability of B given A? So that's basically, you intersect A and B, which gives us only one possibility. And then we have to divide it by the probability of A. That's just marching through the definitions, right? So probability of B given A is probability of B intersected with A divided by probability of A. And B intersected A is just this 2, 4. You see? So then I just have in the numerator 1 over 36 for the numerator, and the denominator is 5 over 36. Maybe this is the most important thing to understand because Markov chains all build on this idea. Okay? So is this clear? And the crucial thing is conditional probability is only defined if the conditioning event can happen with positive probability. Otherwise, we have a division by 0, right? Cannot. So it's always well defined if the conditioning event has positive probability of occurrence. Okay. So this is again just a visualization of when we say the sample space omega shrinking to just the event A. These are the 5 possibilities because we're given that happened. So now we just zoom into that space and work there. And then we know that only this is the one for event B, one possibility, so it's just 1 over 5. So this leads us to maybe the most powerful theorem in the last 100 years, maybe. And this is called Bayes' theorem, right? This is heavily used, everything from autonomous driving to whatever. You know, it's classifiers of all sorts. So what's Bayes' theorem? It's really just conditional probability applied a couple times, right? So, so probability of B given A can be written as, that's the definition, probability of B intersect A over P of A. And then this is just a commutative intersection, so you can flip it around, right? It's the same as probability of A intersect B over probability of A. And then I can just rewrite this, right? So what is this? This is simply, in terms of conditional probability, this is probability of A given B. When I take this term and divide it by P of B, I get probability of A given B. So I just simply apply the definition of conditional probability twice and use the fact that intersection is commutative, and I have essentially what's called Bayes' theorem. So it's very powerful because what it is now allowing you to do is it's allowing you to find the probability of B given A in terms of probability of A given B times the probability of B divided by probability of A. Okay. Okay, so you're supposed to try this at home. Suppose we have a bag of 10 coins. 9 of the 10 coins are fair, but one of the coins has heads on both sides. So what is the probability of getting 5 heads in a row if I picked a coin at random from the bag and flipped it 5 times? If I obtain 5 heads in a row by choosing a coin out of the bag at random and flipping 5 times, then what is the probability that I have picked the 2-headed coin? Now this gets into old problems. My daughter hated the old problems in the Swedish math curriculum. She now knows Swedish much more. Always scared to translate from words to maths. So anyway, this is a good exercise because if you haven't seen this intimately, it's very counterintuitive. So I think I just linked to a bunch of Khan Academy videos. It really marches through these examples, so I highly recommend it. It's just a matter of getting used to the notation. Okay, so let's just do a little bit of simulation in a bit of a hurry, just to get a flavor for this. We will do this more carefully next Friday. So randint question mark should give you this little docstring of, it returns a random integer in the range A to B, including both endpoints. So if I do randint 0, 2 for I in range 15, it will give me a list of 15 numbers between 0 and 2, uniformly sampled. So that's like throwing a Toblerone bar with three sides labeled 0, 1, and 2, right? Cylinder, you roll it and see which side touches the ground and look at it. That's the thought experiment. So let's play with this to get some ideas. So say, let's say Day-1 has randint 1 to 6. Day-2 has randint 1 through 6. Now I just want to print my Day-1 and Day-2, and this time it was 3 and 5. So if I do it again, it's going to be 3 and 2, and so on. So this is like our taste for simulation that we'll do more. So you can kind of construct realizations of random variables in the computer and build intuition this way as well. Okay. So I think we're kind of done with probability. Now we're moving on to random variables. Okay, is everyone happy with this? No? Let's do some quiz. I mean, so what's a good quiz question, Tom? I mean, at the advanced 100 level or 200 level, I don't know, whatever level. I don't know. How do you make sure that everyone's following? So let's see. What? It's not a lot going on for you. So. But I mean, so what's the probability of B given A? So do you guys know, without looking at the notes, what's the definition? Conditional probability.
Probability of A given B into probability of B divided by probability of.
Okay, I want just the definition.
Probability of A given B.
A given B.
Yes.
Yeah.
So I want the definition, right? Are you already spitting the base theorem out? Yeah. Well, that's like applying the definition of conditional probability twice, right? So this is what's going on, right? And what does this mean? This means this thing has to happen. This cannot be 0, right? So this means, so if probability of A is positive, then this is the definition of conditional probability of B given A. Right? And what's the base theorem? We just rearrange this into A intersection B, right? And then I want to rewrite this as, so what's the conditional probability of A given B? Definition. This is just the probability of A intersection B divided by probability of B, right? This is again if probability of B is positive. Right? So I just want this term, so I can just move this guy here. So that's all I plug in here, and I have base theorem. Right? And why is this somewhat magical? It's just because it allows you to express the conditional probability of B given A in terms of the conditional probability of A given B and each of the individual probabilities. And somehow it can allow you to use this basic relationship. Okay, so random variables are our next stopping point because we want to move and start using arithmetic and numbers and so on. So a random variable is nothing but a mapping from the sample space omega to the set of real numbers R, right? In the sort of lowest level. So it's a numerical value determined by the outcome of the experiment. Right? So here we're just looking at real valued random variables, but that's okay for now. So here's the basic idea. So I can say something concrete, roll 2 fair dice, and that's my sample space. And we have everything else, right? We have some probability mapping and so on. But now we have this extra thing that comes along, which is this random variable x. So x now is a mapping from capital omega to the reals. Okay. So for example, instead of the symbols 1 and 1 and 1 and 2 for the face of the dice, I can simply add the face values because these are real symbols, so I can add them. So this is 2, this is 1 plus 2 is 3, 2 plus 1 is also 3. So I have this nice mapping from from the 2 dice to the sum of the 2 dice. And the sum I treat as a real number. This is exactly my mapping. Okay. So I have values this random variable takes, which is integers 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay. So as you notice, 12 has only one particular thing mapping to it, and 2 has only one thing, 1, 1 mapping to it. But then some of these things in the middle, like 6 and 7, 6 has 1, 2, 3, 5 things mapping to it, and so on, right? 7 has 6 things mapping to it. Yeah. And 8 has also 5 things mapping to it. So then I may be interested in example, these things may be my new events of interest, right? What X encodes this sample space as. So that's essentially a random variable. So here's the formal definition of a random variable. So let omega fp be some probability space, so we know that. This is our probability space. And so so then the random variable x is a function from the sample space omega to reals, such that for every real number, every number x, right, such that for every real number x, the inverse image of the half open interval, right, is well defined. So that means, remember x is my mapping, right? It takes points here and moves it there. So you can think of this x as, here's my omega, and there's some kind of a mapping to the real line. And so different omegas go different places. So what I'm interested in is the inverse image of this half open line, right? So if I have x at some point here, so from arbitrary x, I have to look at all the little omegas that fall here. So that'll give me my inverse image, right? That inverse image should be an element of the sigma field. Okay, that's the condition for a real valued random variable. It's too weird. Do you see what I mean? What is this? Minus infinity to x is this whole half line, right? It goes all the way to negative infinity. So I'm including x, and every point in this real line, I look at the set of all omegas. Let's say these 3 little omegas, or these 4 little omegas, map to these 4 points that are all less than or equal to x. So then this set, you see, set of all omegas, this is really the inverse image, right? That's x inverse of this minus infinity to not x, right? So this thing should be an element. This should belong to sigma field. That's the condition. Is this okay? Okay, well, right. So yeah, we'll do. I don't know if I do examples now. Yeah, so let's look at some examples. Here's a discrete random variable. Okay, so a discrete random variable in general can take at most countable sequence of values in the real line, right? So let's look at this one. Yeah, okay, maybe let's look at the sum of 2 dice example first. So so tossing 2 dice and taking x as the sum of the numbers shown, right? So we said that x of 3, 2 is 5, but the outcome 3, 2 is not the only outcome that x maps to 5, right? So then x inverse of 5, this is just one value, right? Just just 5. So if I look at x inverse of 5, it'll be these 4 elements in omega, right? And if I see that as a set, that should be that's one of the elements in my power set. If I look at the finest Sigma-Algebra, right, on these 36 elements. So that's what I'm basically saying here. So now the way you define probability. So here's the probability of a random variable is done as follows. You simply take so if you're interested in what is the probability that the random variable x, takes a value less than or equal to little x, right? Little x is some fixed real number. Then that is simply equal to the probability of the inverse image from minus infinity to x, just pull that back to capital omega. Right? So that's why I want this to be, because probability is only defined on Sigma-Algebras, right? That's why I want the inverse image to be an element of the Sigma-Algebra. That's all that's going on. And this works generally for any real valued random variable, discrete or continuous. And more formally, this is how you think of it. The probability that the random variable x is less than or equal to lowercase x is just the probability of the set of all omega such that x of omega is less than or equal to x. So you kind of have to hold all these little things in your head now, right? So what are we? We're doing experiments. So there's some sample space, capital omega. And then there is now, there's collections here, whatever. So all of these are events, right? These are all elements of, let's call this A, B, and so on. So these are all elements of script f of omega. This is my Sigma-Algebra, right? It's got a lot of conditions it satisfies. And then what I have is my my mapping x. It's actually x of little omega in general, right? And then this takes values in the real line. So here this is 0, all the way is positive infinity, all the way here is negative infinity. So for our die experiment, it was trivial, right? We just had 10 numbers, 1 through 12 numbers.
1, 2, 3,
12.
12.
2 to 12. Just 11 numbers. Okay, so you only took 11 numbers, right? 2, and so on. 12. So okay, I'm just doing this more abstractly, right? So you basically have x of omega, which maps all these little omegas to some real values. And all I'm saying is that the probability that the random variable x takes a value less than or equal to lowercase x is nothing but the probability of the inverse image, right? So what is this? It's any value less than lowercase x, right? So it's the inverse image of this half line, right? So this is the notation. It's open, so negative infinity is not included, but x is included. Everything less than x is included. So this is what I'm after, right? So I invert it back and catch the right thing. Of course, this thing has to be an element of script f of omega. Otherwise, we don't have probabilities, right? Because probabilities are well defined only on events, right? So it has to belong to the collection of events. Well, that's basically it. I mean, and then this gives us my definition of probability of a random variable less than or equal to lowercase x. And that is exactly the definition of what's called a distribution function, df, right? Because you can ask, oh, why are we only looking at values of random variables less than or equal to some real number? What about values that are, in some interval or some unions of intervals in the real line? All those things can actually come from just this elementary definition. So we reserve this capital F to be the special letter. So now, okay, the script F, capital F. So the capital F is a different thing. So capital F of lowercase x is, by definition, this probability that the random variable capital X takes any value less than some arbitrary little x. So that's capital F of x. It's called the distribution function. And if you know the distribution function for a random variable, you know everything about the random variable. Okay, so this is the basic object. I said early on, that when we do non-parametric inference, and you observe a lot of random variables, x1, x2, x3, that are all sampled from some unknown distribution function, capital F, then what we're trying to then do in the non-parametric setting is reconstruct capital F itself. That's essentially, we'll do this formally later. Okay, so here's just a walkthrough of this example for the sum of two dies. So I can say, what is the probability that the random variable x is less than or equal to 5? Right? So that's what is more generally here. So then if I say, what is the probability that that 2 dice random variable is less than or equal to 5, then you have to look at this, pretend this is the number line going vertically. So you have to count, you have to look at the inverse image of all the omegas that fall at 5, 4, 3, and 2. So you just basically go and say, okay, 1, these guys, these blue guys, and this black guy, they're all thrown into a set. That's my inverse image of capital X being less than or equal to 5, right? And that subset is in my power set, which is my Sigma-Algebra example here. So probability is well defined, and I'm all good. So this is the same for pick a fruit at random experiment. So here we have omega is apple, orange, and lemon. And I can ask, I can define my random variable capital Y this time to give each kind of fruit a numerical value. So I can say apple is the number 1, orange is the number 0, and lemon is also 0. I said, because I just, it's my choice. I have to give some real number, so I say this is my random variable. So I'm interested in whether something is not a citrus or it's a citrus. Okay. Okay, so that's my 1 and 0, and then I can again play the same game. My fruit bowls will just map to 1s and 0s, and I can define a random variable Y this way. Okay. This is a slightly more interesting example. So now I flip a fair coin until a first head appears, right? So now I'm flipping forever, right? And then I stop when I observe my first heads. So of course, what I can do, my sample space is the following. Capital omega is just a head, because my first toss, I'll find a head, I'll stop. Or I first toss a tail, and then second one is a head, so I stop, and so on, right? So, and as you notice, this, so now what I can say is my x, my random variable x on this sample space is simply the number of tails before I stop. So x of heads has no tail, so it's 0. X of th has only 1 tail, and this has 2 tails, and so on. Do you see this is a nice real valued random variable, right? And its realization is all the natural numbers, right? 0, 1, 2, 3. And unlike the fruit bowl experiment on the other one, now I have countably infinitely many real values, actually natural numbers that this coin tossing experiment takes. And so those of you who know about this is called the geometric random variable, right? If we assign probability head to be theta, then later on we'll see this is called the geometric random variable, and it's our sort of most basic example of a discrete random variable with countably many possibilities. Geometric random variables already are kind of the heart of population genetic models, the discrete versions of them. So here is a you try at home. So let's see. So here is a fruit bowl experiment. It's here y is defined so that y of apple is 1, y of orange is 0, and y of lemon is 0. So can you use the step-by-step arguments, as in the sum of 2 dice above, to find the following probabilities for a random variable y? So who wants to do this? Because you guys are not doing homework, right? So I have to make you do it. So does someone want to come up to the board? No, not you. So what do we do with this? So my random variable y takes the value 0. Means what? I'm interested in the probability of this event, right? Set of all omega such that y of omega equals 1. Right? I mean, that's this, and this just by definition just the inverse image, right? So what is the inverse image of 1?
It's here, right?
Is it 0?
Yeah.
Oh, sorry, yeah, 0. Sorry. Thanks. Yeah. Good. So then, what is the inverse image of 0? Orange or apple, right? Yeah. Orange or lemon. Okay. Good. So orange or lemon. I'll just put or and L for orange and lemon, right? And these are disjoint events, so we can apply our one of our axioms, right? So this will be the probability of O plus probability of lemon, right? And what is this? How many oranges are there? I don't know. 2 oranges. 2 out of 6. Is that right?
No,
And then this is what?
1 out of 6.
1 out of 6. So basically half the time we're going to get non-apple. Okay, so I think this is a nice walkthrough in Khan Academy on this stuff. And, okay, so I was going to bring this. I have this ankle bone from a kiwi sheep where I used to hike. And so this is a little game people used to play with the ankle bone of a sheep because it only has 4 possible places it can stand, although it has 6 sides. So that's called Astragali, and then you can play. We won't be throwing skull bones here. Maybe the last Friday. So whoever gets the rare side of the bone can buy the beer, Okay, so now we're going to get into implementing random variables. So we saw this. So here is for special classes, so we can extend our proby map, which only works for small sample spaces, but we can basically extend it. So this guy is an RV class, and it's a bit of a constructor. It has some random variable inverse map, proby map, and so on. Okay, it's a bit of work, as you can see, just to tightly do a few things. It also does product experiments, I think, and it sort of defines some operations directly on experiments, but let's just sort of black box this. So, so how can we use this, right? If we encode the random variables into our class. So here I'm just saying sample space is apple, orange, lemon. Probabilities are 3, 6, 2, 6, 1, 6. And then my map X, this is my, what I called Y before. So this says apple is 1 and orange is 0 and lemon is 0. So that's my mapping. And then, so I've defined my sample space, probabilities, and my random variable X. Okay. So then I'm going to declare a variable capital X to be the random variable of these things. These are the arguments to this random variable class that's upstairs. And then I can ask it to give me the string. So say this is the inverse map from random variable to events. And this inverse map, you see, is just a dictionary, right? It's taking 0 and mapping it to the values orange and lemon and 1 to apple. So it just figures that out from the encoding. And so you can do probability of 1. So this is when the random variable takes the value 1. And I don't know. So Jenny did all this when she was doing this DA stuff a while back. So you can kind of ask it to explain the last calculation. It's exactly what we were doing on the board. So the other main thing is different random variables can be defined on the same probability space, right? You just assign different real numbers. So you have a different mapping, and that essentially gives rise to a different random variable. And of course, all throughout under the hood, there was this notion of repeating the experiment, and every time you repeat it, you get a different fruit or whatever, right? And that gets mapped to a different real number for a particular random variable. So the same experiment, you may pull out an apple, but someone else may define a different random variable, say Z, and Z may assign, I don't know, 583 to apple and pi to the other fruits, for example. That's fine. But if that's your random variable, then you can work with this. So in this example, there's another random variable Z, which is mapping 1, 2, and 3. So apple is 1, orange is 2, and lemon is 3. And then the same ideas go through. Inverse images are well defined, and okay, you can just chase it back to the omega and then add the probabilities. So you can ask, what is the probability of this random variable Z for each of them? And the same example with coin tossing experiments. So we can again have my proby map coin toss to be the proby map, which is the one we had last time. And so this is a fair coin toss. and I can have this map 1 head. So this is just a map for a random variable as 1 if the result is head and 0 if it's tail. And so I can call my random variable 1 head and use this class RV. And so now 1 head is this inverse map from random variable to events. So where 0 is tail and 1 is head. Okay. And okay. So the nice thing is the way the random variable class is implemented, Jenny has implemented this power method. So now I can take this new thing, prob map 2 coin tosses, and I can take my prob map coin toss and square it, just apply the square operator, so that automatically under the hood is building a product experiment, so it will do it 2 times and construct all of the stuff automatically. So it's convenient, right? And yeah, so because it's fair, it's just getting quarter automatically from there. And here is now my map heads in 2 tosses, and now I'm having my 2 toss. So 0 is DT, 1 is head and tail. So this is counting the number of heads, right? 2 is 2 heads. So that's a nice power about having classes. So you can, if you have a method for product experiments, then you can raise the mother or father experiment to some power and get the products because these are independent, right? So once again, you can do these things directly. Okay, so that's that. Here's the next major stopping point. So this is called the indicator function of an event. So this is the precursor to the Bernoulli random variable. So we have this bold 1, right? So and then we have the subscript A. So let A be some event in my sigma field, script F. So then I do this experiment, and this function, indicator function, so A, so I have my probability space always, and then I have my event A, right? And what I'm now interested in is whether event A happened. So this is bold 1, and I subscript it with the event, and then the argument is little omega, right? Because something happens. And the question is, so I define this indicator to be 1 if omega is an element of A. So if A happens, this is what I mean by A happening. And it's 0 otherwise, right? If omega is not an element of A. So that's called the indicator function. So the indicator function is clearly a random variable, right? Because it just assigns real numbers 0 and 1. So now we're starting to get into asking questions like, will it rain tomorrow? Yes, from New Zealand notes in the Southern Alps. So that very simple question, we can formulate it to be a random variable. And in fact, I'll try and see if we can do this for Sweden, but I think later on we actually go and fetch the weather station data from one of the New Zealand weather servers. And then you can construct a very simple Markov chain on whether it's dry or wet on a 2-day basis, and the predictions are pretty good, actually. So this type of thing is essentially an indicator function. So here's a sort of deep question, right? So this question of will it rain tomorrow, say in Norway, can be formulated as a random variable, right? So then that really means will raindrops fall on Norway? Okay. This polyline map of Norway, to be precise. So then the question is, can you imagine what the little omegas in the sample space here are? So this is the thing, right? So I'm saying, okay, my event A is, will it rain somewhere? Let's say, will it rain in Norway? And I'm asking now, what is really capital omega now? Huh? Norway.
each point.
Yeah, but the rain has to fall there.
Yeah, but that's if the function is 1. No?
Yeah, but remember, omega is like supposed to be all these things that sort of culminate in the rain falling, right?
Yes, so it's
So it's 1 over 0 multiplied by the number of locations.
No. Okay, guys, this is the most important point. So what I'm saying is, here's some crazy. Remember, we did this omega thing with coin tosses, and I think I screwed up already there. Because even with the coin toss, there's that machine, right? Remember, the machine with the scale, and you put some pressure on it. And I told you that the omega, sample space is only measured like this, whatever, head and tail, right? And now, okay, head and tail is simply 0 and 1, right? So this is 1, this is 0, okay? Right? So this basically is our random variable, right? So this is my x, something like this, okay? I can also turn this to be an indicator function, right? I can say this is the indicator function of head happening, right? That's the same random variable. But what I sort of kept things under the hood is this space, the actual little omegas that are under the hood. And there's a lot going on for the coin tossing experiment, right? Even if you put the metallic strip in a vacuum sealed container, and then you control the electromagnets, and then you make sure the electricity is stably flowing with voltage stabilizers. As much control as you do, all those details that culminate in that flip, right, is encoded in here, right? It depends on how far you want to go. But that's what a physicist or an experimental engineer, this is kind of the state of nature, right? So often we don't go there. So for the will it rain on Norway thing, the capital omega is incredibly complex. It's like all the way the clouds have been moving ever since Earth formed. I mean, it's but you don't go there because it's too much, and maybe it doesn't matter, but it's there. You see what I mean? So, but then you just drop down to this usual representation, and yeah. So you just know there are some omegas that will lead to shower.
Omega like the causes of.
Yeah, So it's yeah. I mean, maybe the Norway experiment is, but the Percy's experiment is very clear, right? It's because it's a completely fixed system, and also the double pendulum, right? Because when you see the double pendulum moving, the table will shake, and so the little omegas will be that specific way the table shook, and how much, tension I had when I released it. My neuromuscular control will enter as little omega as well, right? So that's basically experiments, right? So when Kolmogorov was axiomatizing this, he was working very, very closely with physicists, right? So he would stare at these big vats of glass fluids and glass cylinders heated in different ways from underneath. And then they had glass beads suspended in the fluids, and then they were shining lasers. And so they were measuring the reflection of glass beads. So for him, that motivated his omegas, right? So that was so anyway, normally we don't jump into omegas. It's kind of sacred. You kind of leave it alone, but it's there always. And so, okay, so that's the indicator function. So then the probability mass function is this other definition. It's lowercase f. Remember, capital F was the distribution function, right? So this is called the distribution function, capital F of x. So it's just the probability the random variable x takes a value less than or equal to x. The distribution function, mass function, f of x, is simply the probability that the random variable, capital X, takes on a specific value x. Right? So this is essentially probability of the set of all omegas such that x of omega equals x. So in an experiment like this, this will take some probability, and this event will take some probability. So these are well defined for so-called discrete random variables. Okay, so even like the number of tails you need before you get your first head, that's again a discrete random variable for which the probability mass function is well defined. Okay, so that brings us to our first random variable. That's a parametric family, data parametric family. This is what I've been saying earlier. Bernoulli. Oh, it's long. So here's the Bernoulli random variable. It has this parameter theta because it's unknown. So usually convention is used to use Greek letters for unknown parameters. And it denotes the probability that A occurs, right? So there's some event A of interest. And so you're just using the indicator function to capture whether it's happened or not with 1 or 0. And then when you don't know the probability for the event A, then you call it a parameter theta. And then Bernoulli theta random variable is now this parametric family of random variables with a known probability theta of the occurrence of the event of interest. So we say X is distributed as a Bernoulli theta random variable if the following happens. So theta is a probability, so it's in the unit interval. And then we say its mass function, f of x. So the convention is used to semicolon after x to indicate that the parameter is coming. And all these conventions will matter next week. So this is how you define it, and this is simply theta to the power of x, and 1 minus theta to the power of 1 minus x. And oh yeah. So this is some fancy notation, but what this is saying is x can only be taking value 0 or 1. Okay? And if x takes the value 1, then this will be something to the power of 0, which is 1, so we can forget about it. But this will be theta to the power of 1, which is theta. So that's what this thing on the right side is saying. This simplifies to theta if x is 1. And then the same way, if x takes 0, then this will be 1. And then if x takes 0, it'll be 1 minus theta, and this will be just 1. So it's 1 minus theta if x is 0. And then it's 0 otherwise. Okay, so this is just a switch statement. Now, but the nice thing is it's just this expression. So that's the probability mass function. And then here's the distribution function. It's a typo here. These dollar signs shouldn't be there. So the distribution function is now 1 if x is greater than or equal to 1. And it is 1 minus theta if x is between 0 and 1 and 0 otherwise. Okay, so I think there are pictures of this downstairs. Okay. Yeah. Maybe let's make a picture quickly. So all I'm saying is just lowercase f of x. So 0 and 1, right? So it's going to take the value 1 minus theta. So here's my little bump. So it's going to be 0 everywhere. And at this point, it'll punch tiny hole and jump to 1 minus theta. Right? That's the mass function. And at this point, it's going to punch, again, it'll be 0. It's going to punch a little hole and then just map to theta. Let's say theta is here. Okay. And sum of these two is 1. So this is the probability mass function. And the distribution function is what? For the Bernoulli random variable, capital F of x. So, I mean, this is simply the probability that the random variable x is less than or equal to something, right? So up until 0, it will be 0. And I'm going to punch a hole here. And then I'm going to jump to what? 1 minus theta, right? So that's the actual point. and then it'll continue like this, and then when it hits 1, it'll punch a hole here and jump to theta. I'm sorry, 1. Okay, so this jump will be of size theta. This jump is of size 1 minus theta. So and this continues like this. So this is the distribution function. This is the probability mass function for the Bernoulli theta random variable. And it's a parametric family. So every time theta changes, if theta equals half, these two will be equal, and so on, right? Okay. Yeah, this is again another notation. So sometimes we subscript it by theta instead of putting the semicolon for convenience. Okay, so let's finish this notebook while we are at it in the last 7 minutes, because this will be trivial for you guys. So now I just want to get into for loops in Python, right? It's just like Scala. So I first define my list to be, say, 1, 3, 6, 4, 2. And all I have to do is just do for x in this list, put a semicolon, put a colon, and then I can define my body like this. Okay. So again, you have to keep sure the indentations are correct. Indentations are correct if you have more than one line in the body. And so now I'm basically defining a simple function to print a given list. So this is my function like before. So it takes an argument LL, and then it simply marches through every element for x in LL and prints it. Right? So for this function, yeah, and you note that here I'm starting with 4 indentations, 1, 2, 3, 4, and then I'm adding 4 more here because this is the body of the for loop, and this is the beginning of the body of the function. This is just Python stuff. So then I can just say another list is 2, 24, 24, 46, and then I can simply pass that other list as an argument to this print list function. Okay, so here's a utry. So try first assigning the value 0 to a variable named mySum. And then making yourself a list. You pick what it is called and what values it contains. I don't know. And then looping through the list, adding each element in the list to mySum. So how would you do this? For x in my list, 22 colon x plus mySum. Oh, right. And I want to, the mySum should be the accumulated one, right? So I want mySum to equal x plus mySum. That's what I want. And then I'm going to print mySum. My list 22 is not defined, it says. Oh, probably should execute it. Okay. Lee is looking like I'm gonna kill you. Sorry. Okay, we'll start doing more fancy things, okay, soon, but we can play the same games with other objects, right? You'll start seeing, we'll start playing the same games with primitive geometric objects and other more interesting objects. Okay. So yeah, just familiarize yourself with all this basic syntax. Here I'm just defining a set. And then you can also loop over a set and do something, right? So just do for each s for x in s. I don't know. So it's nice that the for loops can basically go through various containers.
Can also
yeah.
use with parentheses and then I don't remember how they were called. Like things with parentheses instead of the weekend.
Yeah.
How were
I mean, remember we declared sets like this. The set was, you're fine with this?
yeah, so you can, in a for loop, you can put a set.
Yeah.
A list.
Yeah.
There is the other construction that has just.
Oh, that's the dictionary, you mean? The dictionary? Yeah, so you can also loop through a dictionary.
You can start.
Yeah, I mean, but I would probably want to loop through the keys. You know, the dot keys method will give me the keys of the dictionary. I want to loop through the keys or whatever, for items or values. So I think, yeah, this is just a reminder about range. And yeah, this is just making sure you go through these basic statements. So the next one is conditional statements. So we have 2 minutes. I think let's go through this. This is just if-then statements. So with iterating through containers and conditional statements, you can start doing what are called list comprehensions. So that's a very powerful feature in Python. So here is x is 50, y is 40. Then I can say if x is greater than y, do something. So here it says yes, x is greater than y. And if we change these values to be 30, it's not going to go into that conditional statement, right? So conditional statements are quite powerful. So now here is nested conditional. So if I have x, y, and z to be 50, 40, and 60, I want to know if x is greater than y, print x is greater than y. If z is greater than x, print. So, so you know, it will not descend into the second conditional if the outer one is false. So these are some basic conditional syntax, right? Yeah, so, all right, maybe we'll start from here. I don't want to force too much into you guys. Yeah, so we'll start from loops and conditionals, and then I think this leads to list comprehensions later. Okay. So yeah, the coming attraction is we'll get into expectations, data, and statistics. And then I believe a couple more things, and then we'll start doing inference, likelihood principle, and convergence of random variables, and a bunch of things. So is this useful? I don't know. So, well, maybe some Python for you, but conceptually, mathematically, it's 200 level stuff, I think. But yeah, we'll do a bit more next week. And the plan is by week 3, we should know enough about probability and stats to understand sort of the most basic models in mathematical population genetics, which is the module that will continue. Okay.